Alrighty, this is going on page 80. But before we start writing on this, I'm going to write some stuff down. You do not have to write it down. I just need you to stay with me on this. So we're going to talk about what we know about parallelograms. Okay, what we know about parallelograms. So somebody from this table, give me something that you know. Okay, opposite sides are congruent. All right, somebody from this table, give me something. It's a quadrilateral. Okay. Somebody from that table. Give me something about a parallelogram. Anything. Well, okay, just generic parallelograms. Like, yeah, give me like a property of one. I guess that's what. Good. Opposite sides are parallel. All right, give me something from this middle table. Okay. Oh, we have that. Okay, good. Opposite angles congruent. Okay, back there. Well, now you got to change your plan. Come on. Did I ask this before? Yes, the sum of the angles is 360. That's a true statement. So I'm going to say quadrilateral / sum of angles 360. All right. Back there. Give me something. Consecutive angles supplementary. All right. Back there, give me something. You know, you could actually look at your notes. You don't have to, like, stare at me. Just saying. It actually does help. I know you'd be surprised. All right, good. Diagonals bisect each other. Okay. What else? What's missing? Anybody? Look at your notes, people. They're just sitting there staring off the space. Good. If it has one right angle, then it has 4 right angles. Okay. What else? Good. Diagonal divides into 2 congruent triangles. Okay. Is there anything else missing? What? Well, yes, but no. It could just be a generic parallelogram. It doesn't have to be a square, rhombus, or rectangle. It could be just a parallelogram and not be any of those 3 special ones. Oh, well, like a trapezoid's not a parallelogram. A kite? No, not even close. It's not a rhombus. Yeah, it's not. But there is one thing missing from here that's not really necessarily a property, but it is one way to show that what you have is a parallelogram. One pair of opposite sides, what? So, parallel, good, parallel and congruent. Okay. All right, so that's kind of everything we know about just a generic parallelogram, not any of the special ones yet. But let's look at which ones of these things allow us to say that what we have is a parallelogram, right? Because so if it's a parallelogram, all this stuff is true. But if I know just this stuff about a quadrilateral, does that make it a parallelogram, right? So the opposite sides being congruent. If I have a quadrilateral with both pair of opposite sides congruent, yes, that means it's a parallelogram, right? If I just have a quadrilateral, does that mean for sure it's a parallelogram? No, so it's still a property. It just doesn't go in both directions. All right, what if I have both pair of opposite sides parallel in a quadrilateral? Yes, okay, that works. Both pair of opposite angles congruent? Yes, all right. Consecutive angles supplementary. Yes, but it's kind of a little bit easier than that. If I have a parallelogram, I know that any set of consecutive angles is supplementary. If I want to prove that it's a parallelogram, I don't have to show that all of the sets work. I only have to have one angle that's supplementary to both of its consecutive angles, right? So it's not an exact converse, but it does work in both directions. All right, what about diagonals bisecting each other? If I have a quadrilateral, the diagonals bisect each other, it's a parallelogram. What about if I have, like, does this one work to prove that it's a parallelogram? Kind of, but I mean, it's not anything we looked at directly. You could, because if I have a quadrilateral with 4 right angles, what do we know that makes it? A rectangle. And then if it's a rectangle, it is a parallelogram, right? So it's a kind of a roundabout way, and it does work. Probably not the best way, the easiest way to do it. If I had 4 right angles, I would probably use this one instead, just because it might be shorter, but either way it works. It's just not a direct thing. What about just if a diagonal divides it into 2 congruent triangles? If I was going to use, like, if I knew that was true, and I don't know if it's a parallelogram or not, then I could use those congruent triangles to show that I either had opposite sides congruent or parallel or whatever. I'd basically have to use this and go up here and then lead it into something else. It doesn't go directly, but it could get me there. And then this one, yes, this is the one that you don't really think of as a property necessarily, but it is one way to show that you have a parallelogram. Okay? Does that make sense? So remember, on Thursday and Friday of last week, on Thursday we talked about what we know about a parallelogram. On Friday we talked about what do we have to know to show that it's a parallelogram, kind of looking at the converse. So that's kind of what we're looking at today for the special ones. So let's look at what we know about our special parallelograms. If I have a rectangle, I know that all of this stuff is true for a rectangle plus some other stuff, right? So what is specific to a rectangle? Specific properties to just a rectangle. The diagonals are congruent, and the 4 right angles. Okay, opposite sides are congruent. That is true for a rectangle, right? But is that a rectangle property? No, that is actually a parallelogram property, and it is true. And I know that that's something that you've always had, like, tied to a rectangle. So it is a rectangle property. I mean, it's true about a rectangle. It's just not specific to only rectangles. Does that make sense to you? Yes. Okay. So then I have, let's look at a rhombus. So, rhombus. We know that a rhombus is a parallelogram. So all that stuff's true for a rhombus, plus there's 3 things that are specific to just a rhombus. Good. The diagonals are perpendicular. Good. Diagonals bisect opposite angles. And what else? It's true for just a rhombus, isn't it? Good. 4 congruent sides. We all good with that? So then we have square. And it's everything. Is there anything that's specific to just a square by itself? No. There's not a list there because... All right, thank you. It has everything for a parallelogram, plus it has all the rhombus stuff, plus it has all of the rectangle stuff, right? We good with that? So what I want to make sure that you understand also, because I was helping somebody today in math time, is when you are trying to solve these problems and you're looking for angle measures or side lengths or whatever, then you need to think about these properties. Even if it's asking you for angles, think about what the properties are of the sides of the diagonals, because you may need to know that to be able to get the information you need for the angles. So when you get stuck on a problem, you need to go back to your properties that you have, list them out if you need to, or look at your theorems, and make sure that you have everything labeled that you know, even if you feel like it's insignificant, because it may be what you're missing to get you where you need to be. Does that make sense to you? So today, instead of looking at, we know that we have a rectangle, so this is true. We know a rhombus, and this is true, because that's what yesterday's stuff finished up. We're going to look at, these are some of the properties we know. Is it enough to say that it's a rhombus? Basically going the converse way like we did on Friday. Okay, we good? All right, so let's look at page 8. And you need to go to the AP's office. She's one of the secretaries. All right, so this is conditions for special parallelograms. What you want to make sure that you notice from this, I meant to say that back here, is that when the definition of a rectangle says it's a quadrilateral with 4 right angles, okay? But then when you get to the theorem about the diagonals, it says if a parallelogram is a rectangle, blah, blah, blah. It uses the word parallelogram in there. So you have to pay attention to the fact, what is it that I actually need to know? Every single one of the theorems we're going to talk about today starts, if a parallelogram, blah, blah, blah. So in order to show that it is a special parallelogram, you have to first know that it's a parallelogram. Does that make sense to you? It's not just that it's a quadrilateral, but it's a parallelogram already with these extra things. And so that may be something you either need to prove or show, or maybe they just tell you it's a parallelogram. I don't know. But that's an important word here so that we can do this correctly. So this says, if one angle of a parallelogram is a right angle, then the parallelogram is a rectangle. Okay? And that should make sense to you because it says we know we have a parallelogram, right? So that means that this side's congruent to this side. Not congruent, I'm sorry, if that's true. But this side is parallel to this side. And then this would be my transversal. So this angle pair here would be what type of angle pair? What's it called? Same side interior, which means they are supplementary. These happen to be congruent, but same side is supplementary. And since this one's 90, this one has to be 90. So they end up being congruent. Then they are consecutive angles also. Somebody was saying, yes, they are consecutive angles. They are supplementary. They are same side interior. But based on parallel lines, they're same side interior angles. And then, so that makes this one 90. So then these sides are parallel. There's a transversal. These are same side interior angles. So if this one is 90, that one has to be. And you can go all the way around, right? And so you get all four angles being right angles. Plus, we also know that if in a parallelogram, if you have one right angle, you have four right angles, right? So this theorem, to abbreviate it a little bit, would say if you have a parallelogram with one right angle, then it is a rectangle. And because we could use our parallel line properties here and pretty much know that whether or not we had a theorem, I'm not sure that y'all always understand why we have to have a theorem if we could figure that out with parallel lines anyway. If we were truly doing proofs on these things and explaining every single thing and how you know what you know, then to go around the parallelogram like I just did, that's quite a few steps. It's like 15 steps probably to get all the way around, because I would have to say, all right, these lines are parallel, so these are these are same side interior angles, and then same side interior angles are supplementary. Then I'd have to actually add these together and set them equal to 180. Then I'd have to solve for B. Then I'd have to move on to the next one and do the same thing like a bunch of times. Because that'll happen every single time, this one theorem lets me skip all of that. Does that make sense to you? And you don't have to go through the long explanation every single time. All right, so then we have, if the diagonals of a parallelogram, so again, we know it's a parallelogram, if they are congruent, then the parallelogram is a rectangle. All right, so if they are congruent, then it is a rectangle. So we have a parallelogram with congruent diagonals, or with the diagonals congruent, doesn't matter which way you say it, then it is a rectangle. We good with that? And this is important that it's a parallelogram, because if you just have a quadrilateral that has congruent diagonals, it could be a rectangle, but it also could be not just any trapezoid, but I don't know if this is a great picture, but an isosceles trapezoid. So not all trapezoids have congruent diagonals, but an isosceles trapezoid does. And so since it says it's a parallelogram, then it can't be this, because this is not a parallelogram. Not a parallelogram. All right, so then we have one pair of consecutive sides. So one pair of consecutive sides of a parallelogram are congruent. Then the parallelogram is a rhombus. So looking at this picture here, if we didn't know it was a parallelogram, then we may not be able to know that these two sides here are congruent. But because it's a parallelogram, we know in every parallelogram ever that the opposite sides are congruent. So if this side has one hash mark, so does this one. And this one has one, so does this one. That gives you four congruent sides. There's your rhombus. Okay? So a parallelogram with one pair consecutive sides congruent, then it is a rhombus. Everybody okay with that? Then if the diagonals of a parallelogram are blank, then the parallelogram is a rhombus. So the diagonals of a parallelogram are perpendicular. Then the parallelogram is a rhombus. So here's what we know about the diagonals just from it being a parallelogram. Just from it, we know it's a parallelogram. The diagonals bisect each other, right? So if you add to that they're perpendicular, that makes all four of these angles right angles. Then that means all four of these triangles have to be congruent by side angle side, which means that third side that's not marked has to be the same in all of them. And that's where your rhombus comes from. Okay? And that's why that one works. So we have a parallelogram, but you have to know it's a parallelogram. A parallelogram with perpendicular diagonals, then it is a rhombus. Everybody okay with that? All right. So then if one diagonal, and I left off the most important word here, if one diagonal of a parallelogram, that's super important, bisects a pair of opposite angles, then the parallelogram is a rhombus. So we know that the diagonals of a rhombus bisect both pair of opposite angles. But if you're trying to show that it's a rhombus, you don't have to show that it's actually happening to both pair. You only have to show one, and here's why. If we know that this is a parallelogram, then we know that it then we know that opposite angles are congruent. And then since it bisects these, this side's congruent to itself. So aren't these two triangles congruent by angle, side, angle? Right? And then they're also isosceles triangles. So since these two angles are congruent, these two sides have to be congruent. Now we also have a parallelogram with, one set of consecutive sides congruent, but I can make that happen over here too with the congruent triangles. So I have all four sides congruent. It's a rhombus. Does that make sense? So my abbreviation looks like this. We have a parallelogram with one diagonal that bisects opposite angles, then it is a rhombus. Any questions at all? I'm good at this point. Next. All right. So looking at this, it says determine if the conclusion is valid. So this is different than a show question. A show question means we know it's true, show me why. This says determine, which means the answer could be yes, it could be no. And so we have this picture, and then it says EFGH is a rectangle. So based on what you know, do you feel like that is a valid conclusion here? Yes. Okay, so we're going to say yes. And that's because if we have a parallelogram with what? With one right angle, then it is what? A rectangle. Okay. Everybody okay with that? All right, so then what about B? No? Okay. So we have one pair of consecutive sides congruent here, right? So no, go with that, Jacob. What are you saying? What? Right. When you look at that third one down on the front, and if in the way that, I know y'all don't really read questions, you don't even really read instructions or directions, and then you sleep through class like Parker's doing right now, and then you're really confused and lost. But if you just like half read this and you just see, oh, one pair of consecutive sides congruent makes it a rhombus. What's missing there that's important? Parallelogram. You have to know it's a parallelogram before you worry about anything else. Do you know that this is a parallelogram? Do you have enough information to say that it is a parallelogram? No. You also don't have enough information to say that it's not. So I'm not saying it isn't one. I'm just saying I don't know if it could be, but maybe not. I don't know. And so even when we answer this question yes or no, we're not saying no, it's not a rhombus. The question is this valid? And the answer to that is no. This is not a valid conclusion because we don't know that it's a parallelogram, right? So we don't know if it's a parallelogram. And again, I can't say no because it's not a parallelogram because I don't know that either. It very well may be. So what could happen here, since these two sides are congruent, it is possible that these two sides are congruent. And it's possible that it's a rhombus. It's also possible that these two are congruent, but not to these two, and you get a kite. Or it's possible that it looks like this, and it's neither one of them. Okay? So we don't know. If it's a parallelogram, it's going to force it to be a rhombus, but without that knowledge, we're stuck. Okay? We good? Any questions? Got to know that it's a parallelogram. So good job, Jacob. But I knew if I hung on long enough, people would decide that the answer was yes. Are we good? Okay. So then the next part says, use the diagonals to determine whether a parallelogram with the given vertices is a rectangle, rhombus, or square. So again, this is a determine question. We don't know if it could be, we don't know yet. And then it says give all the names that apply. So that's an important thing too. The questions sometimes say that, they sometimes say the best name. If I draw a square and I ask you what the best name for it is, can you put rectangle? Well, you can put it. Are you going to be right? No. Sit up. You, all the way up. Get off the table. Then what if I said give all the names that apply? Would rectangle be in the list? Yes. Okay, so just make sure, again, you're getting the right one. All right, so first says to graph the points. So let's graph these points and label them. So A is at -5, -1, and make sure you put the letter there, and I would put the numbers because it's easier to pull them off the graph than off a list and accidentally get the wrong one. B is at -2, 4. C is at 3, 1. D is at 0, -4. And then we're going to connect the dots here. Now, can I go by the way it looks to know for sure? No, but we still want to graph. All right, so we're going to do the work on the next page. So all we're doing right here is graphing it, and then the step 2 and 3 and 4 is going to walk us through it. Okay. Now, before we determine whether it's a rectangle, a rhombus, or a square, what do we have to know for sure that it is? A parallelogram. Do we know whether or not this is a parallelogram right now? Yes, no, maybe? You said yeah. Okay, we could test it, right? We could find slope and stuff, but do I have to do that? Huh? Or, well, I mean, or do I just know that it's a parallelogram already? Yes. It says, use the diagonals to determine whether a parallelogram with the given vertices. So it's telling me it's with a parallelogram with this stuff. So yes, we already know that. So we're good. So we could find, but we don't need to because it already tells me, so I don't want to do more work than I have to. We good? All right, so now it says, determine if it is a rectangle and state the theorem. Okay, so we have this. We want to determine if it's a rectangle. So what could I algebraically find to be able to determine? Like, what kind of thing would I be looking for here? Okay, so I could find if the diagonals are congruent. What would I have to do mathematically? Okay, are the midpoints going to tell me if they're congruent? The distance, good. If I found the midpoint, it would tell me that they bisect each other, which we already know is true because it's a parallelogram, right? So I could use the distance formula. That totally works. What's a different way to show that I have a parallelogram? What else could I do besides that? Okay, find the slope of two sides to do what? Okay, if I do that, though, I'm going to find, you're saying I want to see if one pair of opposite sides is parallel and congruent. That would give me a parallelogram, which I already know. But I could do something kind of like that to show that it's a that it's a rectangle. What's the other theorem on the front that says that you would know you would have a rectangle? The one right angle. How do I show I have a right angle on a graph? Slope, right? Couldn't I find the slope of two sides and show that they're see whether or not they're perpendicular, and then I have one right angle? Okay, so I could do that, or I could do distance, right? Either one of them would work to show a rectangle. Y'all agree with that? But only one of those two ways is okay right now, right here. Which one and why? The second one, why? Why is that the only one that's okay to do? Well, yeah, but you have that too. Like you've got I could still find the diagonals on the front too, right? If I got congruent diagonals, then it's a rectangle. Because that's the only one I can actually use right now. I can't even use this. Because it says use the diagonals. It says use the diagonals to determine. So if I'm doing the right angle thing, I'm not using the diagonals, right? If it didn't say that, you could use either one and it's fine, right? And slope would probably be a little quicker and a little easier. But because it says diagonals, I have to use diagonals. So also because of that, I want to go ahead and draw them in because that would just help me a little bit. Make sure I'm using the right things here. So let's just go ahead and draw in the diagonals. Yes, so it's BD and AC. That way you make sure you're finding the right thing. Because what I've seen sometimes is that you know you're supposed to be finding diagonals, but you still plug in points to find like the distance, the length of a side, which we don't care about, right? You want to make sure you're using the right pieces. Okay, bless you. So in order to determine if it is a rectangle, we are going to do distance. Distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. And then when you go to do these, don't just find random distance and have numbers there. Make sure that they're labeled because sometimes you need that number again and you didn't even know which was which. Plus, you want to make sure you don't find the same one twice. So we're going to start with AC. I'm going to find the length of AC, and you'll have to look back at your graph to see the points. And I'm just going to look at my graph up here. So to find the length of AC, that's going to give me 3 minus a negative 5 squared plus 1 minus a negative 1 squared. So 3 minus a negative 5 is what? 8 squared plus 1 minus a negative 1 is 2 squared. This is the square root of 64 plus 4, square root of 68. So is 68 a perfect square? No, it is not. So I have to simplify. This could be 2 and 34. And then what? 2 and 17. What do you know about 17? It's prime. So the length of AC is 2 squared is 17. Remember how hard that used to be for some of you? It's not that hard anymore, right? All right, by itself means nothing. Now, I have to go find the length of BD. Am I guaranteed to get 2 squared is 17? No, because it says determine. I may or I may not. If I get 2 squared is 17, then it's a rectangle. If I don't, then it's not. So the length of BD is going to be, let's see, we'll have 0 minus a negative 2 squared plus negative 4 minus 4 squared. So that gives me square root of 2 squared plus negative 8 squared. So square root of 4 plus what? 64. Positive or negative? Positive. So that's the square root of 68. Does that look familiar? Yeah. Do you already know what it should reduce to? Yeah. So we don't have to go through the process again. And we get that the length of BD is equal to 2 square root of 17. All right. So at this point, is this a rectangle? Yeah, you know that. And you know that because the diagonals are congruent, right? Have we said that the diagonals are congruent? No. So you have to explain yourself. You can't just leave this here and be like, oh, it's because they're congruent. Well, we didn't say that. What we found is we ended up with the same number twice, right? So because I know that these are both equal to 2 squared is 17, then I can say the length of AC equals the length of BD. And my reason for that is the substitution property of equality. And that is because I can substitute the length of BD in for 2 squared is 17 over there. Now, that doesn't say that they're congruent either. That says that the lengths are equal. Does that mean that they're congruent? Well, I mean, it's not enough to explain it, but because the lengths are equal, then they are congruent, right? So from here, I can say that, though. Line segment AC is congruent to line segment BD. And anytime you go from equality to congruence or vice versa, that's always the definition. So this is the definition of congruent segments. So now I've said these two segments are congruent. Well, since those segments are the diagonals, means the diagonals are congruent, which tells me that this is a rectangle. So ABCD is a rectangle. And my reason is, because if you have a parallelogram with congruent diagonals, then it is a rectangle. And all of that stuff is your answer. Yeah, you can go before practice. Tomorrow you better go before practice. You can go right now. Hurry. You ain't paying attention anyway. All right. Take the pass. Take the pass. All right. So I want you to think about this. I know that, past this class, you may never have to prove that something is a rectangle again. I get that. You also might surprise yourself. You might have to. But one thing that you should take away from this class, and that is so important to me that you get out of this class, is not just that you can prove that a rectangle is a rectangle, but that the explanation that goes behind it. That you can't just say, well, because it has to be, or because it looks like it. It's your evidence. Just like when you write an essay, and whether it's in a history class or an English class, sometimes you have to have evidence, right? So your evidence is your proofs. It's the same type of thing, explaining how you know what you know and why. That is something that you are going to continually have to do throughout your life. Thank you. You need to go. Now it's you. You need to go to AP's office to see Miss Jordan. She's one of the secretaries. All right. So are we good? Okay. Because the process of having to justify and explain, that is something that is imperative in anything that you do. All right, so now we're going to determine if this is a rhombus and state the theorem or definition that supports our answer. All right, so to try and figure out if this is a rhombus, if one diagonal bisects a pair of opposite angles, that makes it a rhombus. But do I really want to try and look at angles on the grid? No, really don't want to go down that way. So what else could I do? Okay, find the slope of the diagonals and see if they're perpendicular. You agree with that? If it didn't say that I had to use the diagonals, I could also find the length of all four sides and show that all four sides are congruent, right? But I can't do that because it said diagonals. All right, so let's do the slope then. So the slope, we'll start with AC. And we know that slope is delta y over delta x. And that means that's going to be 1 minus a negative 1 over 3 minus a negative 5, which gives me 2 over 8, which gives me 1/4, and by itself means absolutely nothing. So we have to find BD. Now, if these are perpendicular, what do we expect to get for BD? A negative 4. Okay, we're not guaranteed that we'll get that, but we have to kind of have in our mind what we want. All right, so for BD, that means I'm going to get negative 4 minus 4 over 0 minus a negative 2. It gives me negative 8 over 2, which is negative 4. Okay. So what I have here does not tell me that I have a rhombus. What this directly tells me is that they're perpendicular. Does that make sense to you? This leads me to be able to say, because this is true, then line segment AC is perpendicular to line segment BD. Then, because they are perpendicular and we know it's a parallelogram, can we say it's a rhombus? Yes. Good. Oops. So I can say A, B, C, D is a rhombus. And my reason is, if you have a parallelogram with perpendicular diagonals, then it is a rhombus. Okay. Everybody okay with that? Good? Any questions? So then it asks if this is a square. So is there any additional stuff we need to do to show that it's a square? No. The definition of a square is that it has 4 right angles and 4 congruent sides. Now, we haven't officially said that we have that here, except we've said that we have a rectangle and a rhombus, which is basically the same thing. So I can say that ABCD is a square because it's a rectangle and a rhombus. Then it says give all the names that apply. So let's start with the most generic. What's the most generic name we can give this thing? Quadrilateral. Good. Quadrilateral. So then the next most generic would be what? Parallelogram. Then the next two really don't matter what order as far as how generic, but like rectangle. And then what? Rhombus, and then square. Okay. So I want to talk about quadrilateral a little bit more. I want to know what kind of quadrilateral. Yeah, I know it's a parallelogram and all this stuff, but as far as polygons are concerned, it's equilateral and equiangular, so what does that mean it has to be? When it's equilateral and equiangular, what is any polygon? Regular. So this is actually a regular quadrilateral. It doesn't get referred to as that very often, but I do want you to know that it is the same thing, okay? Because it's equilateral and equiangular, it is a regular quadrilateral. When you talk about like a hexagon, okay, it's a regular hexagon. Well, you don't have like a laundry list of things that it could be. It's either it's a hexagon or it's a regular hexagon. That's about as specific as you get. But with a quadrilateral, you got a lot more options here. Okay, we all good? Any questions? Alrighty, we are good.